the FLOW seminar, where FLOW stands for Federated Learning One World Seminar. So this week we have a speaker that's here for the first time, I think. So Liam Collins, he's a third-year PhD student at the University of Texas at Austin. And he works on multitask learning and also federated learning. And today he will talk on representation learning in federated learning. And
yes,
welcome. And yeah, please start whenever you're ready.
Great. Thank you, Sebastian, for inviting me to speak. I'm very excited for this opportunity. So as Sebastian mentioned, I'm going to discuss our recent work studying representation learning and federated learning. And specifically, I'm going to discuss work that draws on two recent papers, one that appeared in ICML in 2021, and one that will appear in NeurIPS this year. And both of these works are jointly written with Hamed Hassani from the University of Pennsylvania, and my advisors, Aryan Makhtari and Sanjay Shakatai from UT Austin. So I'm going to start with a brief introduction to federated learning, as I know most of the audience is already familiar with the setting. So in many modern applications of machine learning and artificial intelligence, data is collected and stored on the edge through a variety of devices such as, or clients such as cell phones, smartwatches, autonomous vehicles, and many more. These clients have insufficient data for training models locally. So we may hope to gather all of the data from the clients in order to train models in a centralized fashion. But this is impractical for many reasons, including the communication costs of transferring data between clients and the central server, memory constraints at the central server, and privacy restrictions on each client's data. As a result, learning must occur in a federated manner across clients, which we'll explain next. In federated learning, we have n clients, each of which has samples drawn from a distribution di, and the loss function for client I is denoted by fi. The central server directs the training process, which consists of sending the current model parameters to the participating clients, and the participating clients executing or updating the received model on their local data and sending the updated models or model parameters or gradients back to the server. Then the server aggregates the models, excuse me, to compute the next iterate. Now, there are many challenges to federated learning, but for this talk, we will focus on the issue of data heterogeneity, or the fact that the local data distributions DI may differ. Excuse me. The presence of data heterogeneity raises a trade-off for each client. In its final local model, to what extent should it rely on information from the relatively large number of samples from other clients whose distributions may differ from its own distribution, versus rely solely on the relatively small number of samples from its own distribution? The standard approach to leveraging this trade-off in federated learning consists of two steps. First, the server learns a single model, theta star, that minimizes the average loss across clients. There are a number of algorithms that aim to solve this objective. For instance, distributed gradient, stochastic gradient descent, or DSGD, fed average, scaffolds, and so on. In the second step, each client fine-tunes the learned global model on its local data before evaluation, with, for example, a few steps of SGD. Naturally, we must ask when it makes sense to take this approach. Clearly, it makes sense if the local distributions DI share some structure, despite being heterogeneous, that can be captured by minimizers of the average loss. A more general question to ask is when it makes sense to implement federated learning in general. And the answer is that whenever the local distributions share some structure that the server can hope to extract, not necessarily by finding a single model that minimizes the average loss. In this talk, we assume that this shared structure is in the form of a shared data representation, or a shared set of important features across clients. Moreover, this representation is low dimensional, meaning it consists of a small set of features that makes it easy to learn a simple predictor or head on top of the representation. More specifically, the output dimension of the representation is assumed to be much smaller than the ambient dimension of the data. Behind this assumption is the classical insight that says in realistic multitask learning problems, tasks with different data distributions nonetheless often share a common data representation. For example, images from different facial recognition tasks often share similar important features such as eye color, jaw shape, and so on. More formally, we can split the model parameters theta into theta phi and theta h, where theta phi are parameters for the representation and theta h are parameters for the head. For example, the representation may be the first L-1 layers of an L-layer neural network, while each head is a different parameterization of the last layer. We assume that there exists a ground truth shared representation theta phi star and local heads theta h1 star through theta and hn star, such that for each client I, the model formed by concatenating the ground truth representation theta rep star, theta phi star, and theta hi star minimizes the loss on client I's data distribution. Our key observation is that when the data distributions share structure in this way, solving the standard FL objective may not recover theta phi star. In other words, we may not learn the ground truth representation with this approach. We'll discuss two ways to overcome this issue and ensure that the ground truth representation is recovered. First, by changing the problem formulation to include learning local parameters. And second, by considering the original formulation, but employing a particular algorithm to solve it. So we first discussed the first approach, namely changing the model formulation. Recall that the standard FL formulation is to find a single model that minimizes the average loss across tasks or clients. And we will show later that solving this objective may not lead to the ground truth representation. Instead, we change the objective such that the goal is to learn personalized local heads for each client, as well as a shared representation. Unlike the standard FL formulation, this formulation is directly targeted at representation learning, since the aim is to learn a shared representation, theta phi, that minimizes the average loss after the corresponding best heads, theta hi, are applied on top of the representation. To solve this representation learning objective, we propose the FedRep algorithm, which takes a natural alternating approach. In particular, the steps of FedRep at communication around T are as follows. First, the server selects a batch of clients to participate and sends the current representation to them. Each selected client receives the current representation and updates their local head for tau h local updates. Then each selected client updates the global representation for tau phi local updates. Next, each client sends its updated representation parameters back to the server, and the server averages the received representations to compute the next iterate. Lastly, note that throughout this process, only the representation parameters are communicated with the server. Moreover, we would like to note that the structure of the representation learning objective encourages a large number of local updates for the head. Observe that the representation learning objective can be decomposed as the sum of n minimization problems with fixed representation and variable heads. So, by running more local updates for the head, we obtain a more accurate approximation of the inner minimization, which means that the subsequent gradient updates for the representation are then more accurate. This encourages tau h to be large for FedRep, meaning that more local updates can be run between communication rounds, which is beneficial for communication efficiency. In order to formally analyze FedRep, we focus on the multitask linear regression setting. Here, each client's task is a linear regression with ground truth regressor theta star I in RD. If clients solve their tasks individually, then D samples are required per client to obtain an accurate solution, which is problematic because D is often large. However, the clients may be able to do better by leveraging shared structure across the tasks. More specifically, suppose that the ground truth regressors for all clients lie in a shared k-dimensional subspace of RD, where k is much smaller than D. Let B star be a matrix whose columns form an orthonormal basis for this subspace. That is, each theta star I can be written as B star times W star I for a ground truth head W star I in RK. Knowing a projection onto the column space of B star, in other words, a ground truth representation, allows clients to solve tasks with only order K samples per task, which is much less than D. Thus, it is advantageous to learn a ground truth representation in this setting. To allow for the possibility of representation learning, the learning model in this case consists of a representation B in our D times K, followed by a head in RK. The population loss for client I is the mean squared error on samples drawn from its local distribution. So now that we have discussed the Federated algorithm and introduced the multitask linear regression setting, we return to the standard FL formulation and compare its properties with the representation learning formulation in the multitask linear regression case. With infinite training samples, standard FL would aim to find a single model BW that minimizes the average loss across clients. Here, the loss for client I is the squared Euclidean distance of B times W to B star times WI star in the population case. Excuse me. Thus, we can show that any minimizer B tilde W tilde of this formulation equals B star times the average of the ground truth heads. Now, infinitely many of these points consist of a matrix B tilde whose column space does not match that of B star. So we cannot recover the ground truth column space using this approach. In contrast, when we learn a global representation and personalized heads, all global minima must satisfy a matrix equation for each client. This means that all globally optimal B hat must share column space with B star as long as the ground truth heads are sufficiently diverse. In particular, they must span RK. So we have determined that the representation formulation is the right formulation for this problem. Now the question becomes, can the Federated algorithm actually solve this problem? And how many samples and communication rounds does it require to do so? To answer this, we must employ the principal angle distance to measure the distance between two linear representations or subspaces, which is the sign of the largest angle between the two subspaces. We can compute this by finding orthonormal bases for the column space of one matrix and the space perpendicular to the column space of the other matrix, and taking the spectral norm of the product of the matrices formed by these two bases. Now we discuss the main results. Here we give an informal version, and the formal version can be found in the paper. The critical assumption is that the client's ground truth heads are diverse in the sense that the minimum singular value of the matrix formed by concatenating them is strictly greater than 0. And we let sigma min star denote this minimum singular value. In other words, the clients have ground truth heads that span RK. Now, based on our prior discussion of being able to choose large tau h, we consider here that tau h is large enough such that each client solves for the optimal head in each communication round based on the current representation and using M samples. Meanwhile, we consider that tau phi is equal to 1. So FedRep essentially here is an alternating minimization between minimizing the loss with respect to the local head and then taking a gradient descent step for the representation So our main result is that if the number of samples M used per client on each round of FedRep is order-wise larger than K squared times D over N plus K cubed log N, then the representation learned by FedRep converges to converges to a principal angle distance of at most epsilon after at most t equal to order log 1 over epsilon communication rounds. So a few remarks are needed to interpret this result. First, the result implies that the total number of samples per client required to reach an epsilon accurate solution in principal angle distance is on the order of d times k squared divided by n plus k cubed log n times log of 1 over epsilon. And this is information theoretically tight up to logarithmic and k factors. Now, once the representation is known, each client and new clients entering the system can find their ground truth regressor with order k samples by retraining their local head. So the end-to-end sample complexity for a client participating in training is equal to the per client complexity of learning the representation, because the order k samples required for learning the head on top of the representation is dominated by the complexity of learning the representation. Meanwhile, the sample complexity for a single client without any collaboration scales with d. So collaboration helps as long as d times k squared divided by n plus k cubed log n is much less than d, which is true for realistic settings where n is very large, and d is much larger than k. Next, we give an overview of the proof. For simplicity, we consider the population case with m equals infinity samples per client and full client participation on every round. Let WTI be the locally updated head for client I on round T. We can show that for some matrix AT that is shared across all clients, WTI is equal to AT times W star I. Now, if we look at the update for the representation BT plus 1, we see that it's equal to a mixture of the prior representation BT and B star. The mixture weight on the prior representation, we call the prior weight, has maximum eigenvalue strictly less than 1 as long as the matrix formed by summing the outer products of the WTIs has minimum singular value strictly greater than 1, or minimum eigenvalue strictly greater than 1. In other words, if the WTIs are diverse, meaning that they span RK, then the matrix of their outer products is positive definite, and the prior weight is a contraction. Now, from equation 1 and the diversity of the W star R's, we have that the WTIs are indeed diverse, as they're equal to a shared matrix times a W star I. So the prior weight is a contraction, and we lose energy from BT in the update BT plus 1. Similarly, we have that the signal weight, or the coefficient of B star, is also positive definite for similar arguments. So the update BT plus 1 adds energy from B star. So this argument shows how the personalized heads, the WTIs, leverage the underlying client diversity in the W star Is to improve their representation in all directions on each round. Next, we investigate the empirical performance of Federated. Here we show results for an image classification on the CIFAR 10 dataset and using a 5-layer and CIFAR 100 and using a 5-layer convolutional neural network. We assign images to clients such that each client has images from S different classes. So the parameter S allows us to control the data heterogeneity, as small s means that the clients are more likely to have differing sets of classes. So the data is more heterogeneous. We compare against local-only training, algorithms which tend to learn a single global model, namely Fed average and scaffolds, and their fine-tuned versions, and a variety of methods that aim to find personalized heads and personalized models in federated learning. In the 3 columns shown here, we vary N and S. Additional experimental results and details can be found in the paper. But the first observation is that in all cases, FedRep achieves the highest or second highest test accuracy. However, the second observation is that Fed average with fine tuning also performs very well. Now, in Fed average with fine tuning, again, we first train a single shared model to minimize the average loss over tasks. Then we fine tune this model on each client before evaluation. So now we have some discussion. We've shown that Federated provably recovers the ground truth representation at a linear rate with efficient samples per clients and achieves high test accuracy on neural networks in practice. However, we additionally observed that Fed average plus fine-tuning also performs well empirically, which is surprising since it tries to optimize the standard FL objective of finding a single model that minimizes the average loss across tasks. And we have already argued that minimizing this loss may not lead to representation learning. We next attempt to explain this surprising behavior by taking a closer look at Fed average.
Okay, so let's maybe ask the audience if there are some questions on the first part of the talk, because I think you're now skipping to the to the second paper. So is there any question from the audience on this? And then maybe a question from me. So how did you, for the experiments, maybe I missed it, but it seems to me you need to set this parameter. No, you need to set how many parameters are shared and how many parameters are like in the head. So did you just take the last layer of the model, or was there some...
Right, yeah, good question. So yeah, we only took the last layer as the personalized head for FedRep. And okay, the rest was shared.
Yeah, but you could also play with maybe sharing just fewer layers or more, but you don't know how much impact this has. Or...
Yeah, you have to tune this parameter. Yeah.
That's good. Okay, so I think, okay, there's no question from the audience, so let's go on and take maybe questions then at the end of the talk. That's
sure, great.
Thanks.
Okay, so first let's provide a quick review of Fed average. So to find a single model theta that minimizes the average loss across tasks or clients, Fed average executes an iterative procedure in which at the start of each communication round, the server sends the current model parameters theta t down to a batch of selected clients. And then each selected client executes multiple steps of SGD or a similar gradient-based update procedure on its local data before sending its updated model back to the server for averaging. Now, the motivation for executing multiple local updates between rounds is communication efficiency, as it allows the total number of updates to be much larger than the number of communication rounds. This makes Fed average more communication efficient than its counterpart distributed SGD, which executes only one local update between communication rounds. However, local updates complicate the behavior of Fed average from an optimization perspective. In particular, local updates can cause local models to drift away from global solutions in data heterogeneous settings, since local gradients are not necessarily aligned with global gradients. This phenomenon has been well studied. Many works have shown that Fed average with fixed step size may not solve its intended objective of finding a single model that minimizes the average loss across clients in data heterogeneous settings because of this local client drift over multiple local updates. In these cases, Fed average solves some unknown objective inconsistent with the standard FL objective. Now, the literature has proposed many methods to correct Fed average's local drift and objective inconsistency. These methods employ various techniques to control the local updates and ensure that the single learned model, in fact, minimizes the average loss across clients. In this work, we propose a different understanding of local updates, namely that they may be good for generalization, despite being bad for optimization. Indeed, we've already seen that running Fed average and then fine-tuning the single shared model on each client's training data leads to test accuracies competitive with state-of-the-art personalized federated learning algorithms. The fact that Fed average does not actually solve the standard FL objective, which we have shown may not lead to representation learning, it could mean that it instead solves some other objective that prioritizes representation learning and generalization. Here, we give empirical evidence suggesting that Fed average's multiple local updates between rounds are indeed critical to its ability to generalize to new clients, even in data heterogeneous settings. In the left plot, we trained Fed average and distributed SGD on the first 80 classes of CFAR 100, with C classes assigned per clients. Thus, the smaller C, the more heterogeneous. Fed average makes 50 local updates per round, and DSGD makes only 1 local update per round. For fair comparison, DSGD executes 50 times more communication rounds than Fed average. So both algorithms make the same total number of communication of local updates across communication routes. After training, the learned models are then fine-tuned on new clients constructed with data from the 20 remaining classes from CFAR 100, with varying amounts of samples used for fine-tuning, excuse me, shown along the x-axis. The test accuracy is then evaluated with new data from those clients after fine-tuning. As we can see, the fine-tuned Fed average models achieve roughly 10% higher test accuracy than the fine-tuned DSGD models for all amounts of fine-tuning samples. The plot on the right shows a similar story. Here, the models are trained on all of the classes from CFAR 100, then fine-tuned on new clients constructed from the 10 classes in CFAR 10. Again, Fed average achieves roughly 10% higher test accuracy than DSGD post fine-tuning. These results suggest that local updates are not only essential for communication efficiency, but are also somehow necessary to capture the shared structure among heterogeneous data distributions when learning a single model. Next, we empirically investigate whether representation learning is indeed the mechanism by which Fed average is generalizing well after fine-tuning. To do so, we measure this. We measure the centered kernel alignment similarity, or CKA similarity, of the model layers before and after fine-tuning in the experiment from the right plot on the previous slide. CKA similarity is a standard metric used to evaluate the similarity between neural network layers. Here in this plot, the model layer varies along the x-axis. We see that for Fed average, the early model layers have very high CKA similarity, close to the maximum value of 1. Since these layers correspond to the representation layers, this suggests that the Fed average representation does not change much during fine-tuning, meaning that the representation learned during training has already captured the important features for the data from the new clients, and is therefore already expressive enough to allow for high test accuracy after fine-tuning the later network layers. On the other hand, DSGD needs to significantly alter its pre-trained representation during the fine-tuning process, as the CKA similarity between its pre-trained and fine-tuned model is relatively small, even in the early layers. This suggests that DSGD has not learned the important features shared during clients during training, unlike Fed average, or at least it has not learned as many of the important features, or to the same extent as Fed average. Despite this empirical evidence of Fed average's representation learning ability, to the best of our knowledge, no prior works have shown whether Fed average is in fact capable of learning effective representations, nor have they proven whether local updates are indeed necessary for representation learning. We studied these questions by again considering the multitask linear regression setting. Recall that in this setting, each client's task is a linear regression, and the ground truth regressors for all tasks can be written as the product of a ground truth representation B star and a ground truth head W star I. If we know the column space of B star, we have reduced the regression problem from D dimensions to K much less than D dimensions. So we will only require K order K samples to solve it. So it is therefore imperative to recover the column space of B star. Here, the standard FL objective is to find a single representation B and a head W that minimize the average loss over clients, which in the population case is simply the squared Euclidean norm of the difference between B times W and the ground truth regressor for client I. Now the question is, does Fed average recover the ground truth column space when run on this objective? Our main result again relies on the client diversity assumption, which says that the ground truth heads span Rk. We prove that running Fed average on client population losses with at least tau equal to 2 local updates between communication rounds learns the ground truth representation at a linear rate. In particular, Fed average learns a representation that is principal angle distance at most epsilon from the ground truth after at most log 1 over epsilon divided by alpha squared tau sigma min squared communication rounds. To our knowledge, this is the first result proving that Fed average learns an effective representation in any setting. Before discussing how to prove this result, we first illustrate why the proof is difficult by showing that one cannot complete it using arguably the most natural approach. So recall that the local population objective for client I is to find a matrix B and a vector W whose product BW approximates the ground truth regressor B star WI star. For ease of notation, let B hat I and W hat I denote the result of tau local updates for client I. Now, the naive idea is to use the fact that if we have local convergence, in fact, if we have perfect local convergence, meaning that B hat I times W hat I is equal to the ground truth regressor for client I for all clients, then the local products after these local updates all lie in the correct subspace. And moreover, the span of these local products is exactly equal to the column space of B star, as long as the W star I's are diverse, which we assume to be the case. So if the server were to compute the next representation BT plus 1 by finding an orthogonal basis for the span of the local products, we would exactly recover the ground truth column space. However, this is not how Fed average computes BT plus 1. In contrast, Fed average computes BT plus 1 by simply averaging the local representations. Unfortunately, convergence of the local products does not imply that the average of the local representations is any closer to the true representation, as we will see on the next slide. We consider a heavily simplified two-client scenario to illustrate this. Let there be two clients and k equal to 2. The ground truth regressor for client 1 is the first standard basis vector in RD, and the ground truth regressor for client 2 is the second standard basis vector in RD. Thus, the ground truth representation is the subspace spanned by the first and second standard basis vectors. Next, suppose that the local updates converge to the corresponding ground truth solutions. Without using any other information, it could be the case that the locally updated head is equal to the same vector for both clients. Here, the 1, 0 vector. This means that the locally updated representations contain the information about the column space of B star obtained by solving the local problem in the first column for both local representations. Thus, when these representations are averaged in the Fed average global update, the results will lose information about the column space of B star and become rank 1, meaning it is orthogonal to the ground truth subspace in one direction. Thus, we cannot rely solely on local convergence in order to complete the proof. We must leverage other properties of the dynamics. To do so, we execute a direct analysis of the local update, or of the global update BT plus 1. This update is quite messy as it is the average of locally updated representations for tau gradient descent steps. But we can show that the update roughly boils down to a similar form as in our previous update of BT plus 1 for FedRep. That is, BT plus 1 is approximately equal to the sum of BT times the prior weight plus B star times the signal weight. The prior weight is again a contraction as long as the locally updated heads are diverse across clients for at least one local iteration S. In fact, we will show that they are diverse for all tau minus 1 local updates besides the first local iteration, which results in the tau term in the denominator of the communication complexity. Similarly, if the local heads are diverse, then the signal weight is positive and replaces the lost energy from BT with energy from B star in the update of BT plus 1. So it remains to show that the local heads, denoted WTIS, are indeed diverse. And S here is an index over a number of local updates. So to show that these local heads are indeed diverse, let's take a closer look at the update of the local head after the first local iteration. So WTI1 is equal to one gradient update starting from WT, which we can show is equal to a shared term, which is I minus alpha BT transpose BT times WT, plus a unique term, which is alpha times BT B star W star I. So the shared term is the same across all clients. So this is not diverse. Whereas the unique term is unique to the ith clients because it has the W star I. So in order to show that the WTIs are diverse, we want the unique term to dominate. So we can show that the unique term dominates by showing that the matrix delta T defined as I minus alpha BT transpose BT is approximately equal to 0. And since the WI stars are diverse, then the WTIs are also diverse, meaning they span RK. And we can continue this argument for all subsequent local updates. That is, if the delta matrix remains small over the course of local updates, then the unique term continues to dominate and the locally updated heads remain diverse. Now, the most challenging part of the proof is showing that the delta matrix indeed stays small, both over the course of local updates and over the course of global updates. So in order for delta T to remain small, BT effectively must be a scaled orthogonal matrix or close to a scaled orthogonal matrix. Now, it's not clear how, even despite global aggregation, global averaging of the local representations, the result of this averaging would remain close to a scaled orthogonal matrix. However, we're able to show that this is the case, and so the locally updated heads continue to remain diverse after one local update for all communication routes. So please see the paper for more details on this induction. But in summary, the analysis reveals that the local heads become diverse after one local update due to the underlying client diversity that's captured in the W star I's, which in turn, as we saw in the previous slide, leads to representation learning due to the update of the structure of the update of BT plus 1. So now suppose that tau is equal to 1 and we have the update of DGD. And again, we consider the population case. We can see that the update of BT plus 1 again has this form where it's equal to BT times the prior weight plus B star times a signal weight. However, unlike for Fed rep and for Fed average, here the prior weights is not a contraction, as the negative term in the prior weight is only rank 1. And the signal weight is not positive definite, as it is only rank 1. So because of this update, the prior weight can contract in only at most one direction. And the signal weight can only add energy from B star in at most one direction. So the representation can only move closer to the ground truth column space in one direction on each iteration. And so it's not clear that it can eventually reach the ground truth column space. And in fact, we prove that that DGD cannot guarantee to recover the ground truth column space in this setting. So the idea is that the behavior of DGD is identical for two B stars which align in the one direction that it is learned by DGD, but are almost orthogonal in other directions. So if DGD converges to one of these B stars, it must diverge from the other. And most importantly, this result confirms that local updates are indeed necessary to representation learn. Now we run simulations of the multitask linear regression setting in order to highlight the difference between the optimization perspective and the generalization perspective of understanding federated learning alluded to earlier in this talk. So from an optimization perspective, existing theory as well as our simulations show that DGD converges to a stationary point of the standard FL objective, while Fed average does not, as shown in this plot. However, from a generalization perspective, Fed average learns the correct representation, as shown on the left, and as shown on the right, achieves smaller mean squared error after fine-tuning on new clients, as shown again in the right. In contrast, DGD is not able to learn the representation and generalizes much worse than Fed average to new clients, as shown on the right. So these plots illustrate the main message of our results. That is, local updates can lead to better generalization through representation learning, despite causing Fed average to fail to solve the standard FL objective. We close with some discussion. So we have showed how two federated learning algorithms, FedRep and FedAverage, learn shared representations in data heterogeneous settings. In both cases, the key parts of the analysis were to show that the local heads captured the underlying diversity of the ground truth heads to improve the representation in all directions. For FedRep, the local heads are able to capture this diversity because the formulation calls for personalized heads. On the other hand, for FedAverage, the formulation calls for a single global head, yet the algorithm is able to obtain diverse local heads that capture the underlying client diversity through multiple local updates. These results suggest that it is beneficial to study federated learning algorithms' ability to recover a ground truth model or ground truth features in order to understand their generalization performance. As we have seen, that generalization on new data and clients is directly related to the algorithm's ability to capture ground truth features shared among the clients. Finally, our work raises numerous open questions and avenues for further research, including analyzing the roles of local heads, local updates, and client diversity in learning shared representations in nonlinear settings, such as shallow nonlinear neural networks. Second, extending our representation learning framework to settings in which the ground truth features may be shared at different stages of the network, such as in the later layers as opposed to the early layers. And finally, understanding how representation learning is affected by practical challenges in federated learning, such as system heterogeneity, which can cause asynchronous global updates of the representation, and the need for model compression, which can prune or quantize some representation parameters with the aim of improving communication efficiency. We leave these questions for future work. And with that, I will conclude my talk. And I'd like to thank the audience for listening, and I'm happy to answer any questions at this point.
Okay, thank you, Liam, for this interesting talk and also very, very technical. And so we have, I don't know, let's see. So I asked also in the chat if there's some questions from the audience. It would be a good time just to raise your hand and then we can unmute you, or if you type it in the chat, I can read it out. So maybe before people made up their minds, so can you, maybe I missed that. So the first paper, no, that was really clearly dependent on this parameter K. You needed to know it because you design your algorithm in this way. And now this second part, you just say, oh, you analyze standard federated learning. And this distinction, what is the head, what is the shared representation, does not need to be known to the when you run the algorithm, or do we need to know it somehow implicitly? Or
yeah, our results rely on knowing K even in the standard FL case in the second half of the talk. Yeah, so this right. So to show that Fed average can learn the ground truth representation, it needs to have a model that has the capacity and has the same dimension as the ground truth representation.
Mhm.
But certainly I think this could be extended to cases where the dimension of the parameters is larger than the ground truth dimension. So yeah, this would be another point for future work.
Okay, and how difficult do you think is it? It will be to sort of extend some of your results to, let's say, a nonlinear setting where we have maybe again a neural network as the representations and not just this matrix B. So what is
right? Yeah. So the I mean, it comes down to the fact that even in these nonlinear settings, each client should have some subset of information about the ground truth representation. So if the local gradients for each client have this information, which in aggregate across all clients can give the full representation, it should be possible to extend these results to nonlinear settings. Yeah, so I mean the analysis will be more complicated because everything simplifies nicely or somewhat nicely in the linear case, but I think at least in principle, like as long as there's as long as each client is contributing a subset of the entire information that is needed to learn the ground truth representation, yeah, the ideas should hold. But we haven't analyzed these cases yet, so it's hard to say exactly.
Yeah, okay. Yeah, okay, thanks. Okay, so there is not so much. Okay, there is one question from Virendra. I will just allow you to sort of ask to unmute. Okay, so you exactly, maybe you could ask in the chat. Yeah, perfect.
Yeah, I wanted to extend your question, Sebastian, to something like differential privacy, and how would that affect the results, or how do you have any insights into an application of your results in the presence of differentially private federated learning?
Right. So if the updates have noise added to them to ensure differential privacy, I mean, I think it would just be a matter of bounding the effect of this noise. I mean, like the information about the ground truth representation should still be there. It will just be harder to recover, but still, yeah, it would just be about bounding the effect of this noise. But I'm not an expert on differential privacy, so yeah, it's hard for me to say exactly. But yeah, this is something to consider. We didn't consider any formal privacy guarantees in this work. So yeah, thanks for bringing that up.
Okay, so we have another question by Pedro in the chat. So if it's maybe a bit in the similar direction. So he asks, from the perspective of an attacker that wants to extract your model, perhaps, I mean, is it somewhat easy to maybe, can differences between representations be obtained? I don't know if some models are corrupt or due to data heterogeneity or so, but did you look a bit into that, or can you comment on this?
So, right. So, can differences between representations be obtained due to data heterogeneity or corrupted models? So, if yeah, I mean, I haven't looked into this model text scenario. So yeah, I'm not sure. Yeah. It's okay. So I'll move on to the next question, if that's okay. Yeah. Okay. So I'm at first.
It's also, we can maybe handle this offline. I had one more comment. What is it now?
Oh, thank you.
Okay, so maybe to summarize a bit, no. So you say, no, okay, we should use federated learning because it optimizes badly, but it learns these representations. I know sort of the community has worked a lot on coming up with better algorithms, let's say, to address data heterogeneity and so on.
Yeah.
So do you know, or have you tried to see, let's say, if you run scaffold or something, would it learn weaker or not so good representations, or will it still work, or what is it?
Yeah, this is a very interesting point. So we haven't had a chance to look into this yet, but right, it is interesting because scaffold will solve will actually minimize the average loss across clients, unlike fed average in data heterogeneous settings. However, fed average is still, or sorry, scaffold is still doing multiple local updates. So, so there's a chance that through these multiple rounds of local updates, scaffold could still learn the representation. So our only negative result is for DGD, so one local update. So if you do have local updates, even if you still exactly solve that that standard FL objective, you may still be able to learn the representation. But yeah, this is something that would be interesting to investigate further, for sure.
Okay, so thank you, and I think it's a good time to end the at least the live or video part of this presentation. So thank you again for joining us here. It was really nice to see exactly a bit of different aspects, but also good to see some different advantages of this federated averaging algorithm. So and also to the audience, thanks for joining. So